Hi everyone, I'm Xie Junfeng from Huawei. Today, I'm very honored to share with you some of our works, our team's work about porting OpenJDK to RISC-V. In this talk, I will first give you a brief introduction about me, about the work we have done, and about why Huawei is so interested in RISC-V. And next, I'll choose some of the work and give you more details about them, about the challenges we faced and the solutions we provided. Among them, I will spend the most time on our explanations on pointer masking. Hope you will find it interesting and informative. First, let me give you some brief introduction about me, about the team. My name is Xie Junfeng. I have graduated from Fudan with a master's degree for 1 year. I joined Huawei as soon as I graduated, so this is my second year on this job. Last year, I was mainly involved in the development about RISC-V 32.0 and TBI, which is related to pointer masking. That's why I'm going to talk more about the pointer masking today. And our team is the owner of OpenJDK RISC-V port. You can visit the repository via the link below. And these are some of the leaders, committers, or authors of RISC-V port from Huawei. In case you don't know, RISC-V is an open and free instruction set architecture that supports various processor designs. It is modular, meaning it can combine different base and extension instruction sets for different application scenarios. It is also collaborative with a large member organization and open source community that drive its progress. You may ask why we tried to port OpenJDK to RISC-V, or why Huawei is so interested in OpenJDK and RISC-V. This is because first, a large number of Java services are running in Huawei. And second, we provide some self-developed hardwares like Quimpen CPU. So we need to optimize the JDK on our own hardwares. And third, RISC-V is free and open, and we have some further explanations based on RISC-V. Here I list the work we have done. On the right, you can see there are many extension instruction sets in RISC-V. We have supported RV64 IMAFDCV, in other words, integer multiplication and division, atomics, float, double, compressed instructions, and vector. We have also supported ZBA, ZBB, ZICSR, and ZFSI. I'll discuss some of them in detail later. And we provided support for Zero template interpreter C1 and C2. We supported all GC algorithms, including ZGC and Shenandoah. We supported Zero for RISC-V 32. And we supported a virtual thread on JDK 20 and following function and memory API on JDK 21. And we also supported generational ZGC. In fact, generational ZGC is still in progress, and the ZGC team plans to release it in JDK 21. So we ported RISC-V in their own repo. And our plan. Now we are backporting our work to JDK 8, 11, and 17, and we plan to support Vector API in the future. By the way, you are probably wondering, since these extensions are optional, what if the current system does not support the extensions? And how do we know if we can use the extensions? In fact, we add many VM options, and you can turn them on in your command line if the current machine supports the extensions you want. Also, we can check if the extensions are available at runtime. When the VM options are turned off, we will still generate the code, but only via the base instruction set. The following two figures show the performance on SpecJVM 2008 and SpecJBB 2015. On average, our RISC-V port is 39 times faster than 0JDK, based on SpecJVM. And on the right is the score of SpecJBB 2015. We do not give a performance comparison here between 0JDK and 0JDK because we failed to run SpecJBB on 0JDK. 0JDK is too slow. Now I start to share some of the work we have done for porting OpenJDK to RISC-V. First, I'm going to share you about the difference between RISC-V and other architectures on flag register. Not like other architectures, there is no flag register in RISC-V. This is because RISC-V uses a single instruction to implement the compare and jump operation. As you can see here, the BEQ instruction of RISC-V requires 3 parameters, OP1, OP2, and the address or offset to jump or branch. In some other architectures, you have to first compare the 2 operators and store the result in the flag register, and then determine whether to jump based on the flag register. So the difference brought us some challenges that some top-level designs of C1 and C2 are based on the flag register, and it's hard for us to get around these restrictions. For C1, there are 2 LIR code called the CMP and branch. Usually CMP and branch come in pairs, and a branch always appears after a CMP. But as I just mentioned, RISC-V has no instructions corresponding to the 2 LIRs respectively, because a single BEQ instruction can do both compare and branch. Our solution is that we do nothing but save the 2 operators temporarily to the these 2 variables, CMP OPR1 and CMP OPR2, when we get a CMP code. After some time, when we get a branch code, we consume the 2 operators we saved before. That is to say, we move the operation of compare to branch. We do the same thing when we got CMove. But for C2, the situation is different. There are some top-level design limitations in its IR, and sometimes we cannot use the same way as we did on C1. In OpenJDK, T1 register and T2 register are not used. So in such cases, we let the T1 register play the role of the flag register. That is, first we do the comparison and store the results to T1 manually, and later we consume the result in T1 when needed. In fact, T1 is not completely unused during the entire runtime, but we have already taken care of all the places where T1 is used for other purpose. Next, I want to talk about a problem about weak memory ordering we met. The memory consistency model of RISC-V is the RISC-V weak memory ordering. So RISC-V does not guarantee that stores to instruction memory will be made visible to instruction fetches on a RISC-V heart. Here, heart means hardware thread until a fence.i instruction is executed on that heart. Here I mentioned a term heart. In RISC-V, we use the term heart to concisely describe a hardware thread as opposed to software managed thread contexts. It's similar to the logic core on other ISAs, but they are not exactly the same. And note that a Java thread is not bound to a specific heart. So because fence.i only orders stores with heart's own instruction features, application code should only rely on fence.i if the application thread will not be migrated to a different heart. So it doesn't ensure visibility to other RISC-V hearts in a multiprocessor system. Let's take a look at this example. At the beginning, thread A ran at heart 1. Then some code was modified and fence.i was invoked. But after that, for some reason, your thread A got rescheduled by kernel to heart 2. Therefore, when thread A executes the following code, it may execute old code that is not flashed on heart 2. Therefore, only executing fence.i on the current heart cannot fully achieve the effect of flashing a cache. Our solution is to use the flash iCache syscall. At the very beginning, we put fence.i before the relocatable code, and we also invoke flash iCache when the code is modified. But in this situation, in this solution, we don't have to do anything on read hearts. As you can see, we have a patchable code here on a read heart, and we don't choose to put a fence.i before it. All we need is to call the flash iCache syscall after modifying the code on the right heart. In the syscall, it not only invokes fence.i for the current heart, but also calls an IPI and makes all other hearts also invoke fence.i. So now you can understand why we removed the fence.i before the relocable code on the read hearts. We do call fence.i on read hearts, but just by way of API. After all hearts finish executing the fence.i, they all continue with the new code. So as you can see, this syscall is a time-consuming operation. We didn't test the performance change before and after removing the fence.i on the read hearts because it's obvious that we reduce one instruction and of course it will be better. On the next page, I'll talk about the V extension. Here V means Victor. Hotspot has supported SLP for auto-vectorization. And most architectures like x86, ARM, and MIPS provide SIMD instructions to do some vectorized parallel work. So SLP is usually implemented by SIMD. But the RISC-V designers didn't choose to implement SIMD instructions, and instead, they created an extension with vector instructions. They didn't choose SIMD because it's incremental design and it only supports fixed size vector. For example, the IA32 instruction set has grown from 80 to around 1,400 instructions since 1978, largely fueled by SIMD. For another example, this is the vadd instruction for byte vector in ARC64. You have to use different instructions for different widths of data. Anyway, for a variety of reasons, the designers created the RISC-V vector to replace the role of SIMD. Its benefits are that it can generate fewer instructions than SIMD and hide the implementation details of the CPU. But for us, the difference is porting SLP. The difference in porting SLP is that rather than encoding width directly to the instruction, RISC-V vector extensions using vset VL these instructions to set vector width for subsequent vector instructions. As shown in the figure, we set the type and the length before we invoke the vadd. In short, the vector instructions of ARC64 include data width, while vector instructions of RISC-V do not. Instead, the data width needs to be set with an additional instruction. In fact, there is still one optimization to do that we don't have to set the width every time before we call the vector operation. One way is to do the peephole optimization, but more generally, we can analyze the control flow and the data flow and create a vector length node to determine whether to insert vset. You might want to know what the performance is with support for V extension, but in fact, there is no hardware with V extension yet. We perform the functional verification on Qumio, so there's no benchmark data yet. By the way, if your platform doesn't support the V extension or you have turned off the VM option, use RVV, we will still generate the code for you, but only via the base instruction set. And next, I'm going to talk about the B extension. The bit manipulation extension collection is comprised of several component extensions to the base RISC-V architecture. This extension is intended to reduce code size and improve performance. We have supported ZBA, ZBB, and part of ZBS. In this section, I'll just give you two examples to let you understand more intuitively. The first example is REVB8, which means reversing 8 bytes. In Java, there is a method called reverse bytes in class long. This API is to reverse the byte order of the long integer. Following assembly code is generated by C2 compiler. As you can see, there are 23 instructions with 5 temp registers. But with B extension, we can do the same thing with just one single instruction, REVB8, and no other temp register are used. The B extension also provides shift and add instructions to accelerate the generation of address that index into arrays of basic types. Here is one common scenario to modify elements in array. Without sh2 add, we need 6 instructions, but with sh2 add, we only need 2. Here is the code size reduction of B extension on StackJVM. The data is based on B extension version 1. From the data below, the geometric mean code size reduction of B extension for StackJVM is 2.9%. Again, the data is based on Qumio because there is no hardware that have implemented it. The rest of the time, I'll discuss some of our team's experiments and thoughts on the J extension. Here, J means JIT. The RISC-V J extension aims to make RISC-V an attractive target for languages that are traditionally interpreted or JIT compiled. One of the most important proposals in it is pointer masking. RISC-V pointer masking is a feature that, when enabled, causes the MMU to ignore the top n bits of the effective address. Note that this extension has not yet been released, So there is no hardware and even no QEMU. So the following experiment was not performed on RISC-V platform. In fact, we did this experiment on ARC64. When RISC-V pointer masking is released, we will also be able to do the same experiment on RISC-V. With this feature, we can do many things. Today, I mainly talk about one of the most important applications of pointer masking, which is tagged pointer. Generally speaking, tagged pointer, or also known as address tagging, means folding a few bits as additional data into a pointer or memory address. Such tags can be used by managed language runtime systems for various purposes. For example, we can store GC state and data type in tagged pointers. The advantages to use tagged pointers are obvious. Memory of allocating a tiny object can be safe, and a load can be reduced. But the disadvantage is that there may be a price of the dereference. On the right, I've given 3 cases of tagged pointer. In Objective-C, the top bit is set to 1 to indicate that this is a tagged pointer. In this case, you can visit the tag and extended bits. The top bit must always be 0 for a real pointer. In JavaScript version 8, a value is either a pointer or a small integer, SMI. The engine uses the least significant bit to distinguish the small integers from heap object pointers. If the bit is set, the engine uses the top 32 bits to store an integer. And in ZGC of JDK, a tagged pointer is also called a colored pointer or Z pointer. ZGC reverses the lower 42 bits for the actual address of the object. The next 4 bits are used for these flags, marked 0, marked 0, marked 1, remapped, and finalizable. And the remaining high bits are all 0. Tagged pointer is just a concept, and there are many ways to implement it. You can dereference a pointer manually before accessing it, but you have to pay for an extra instruction. We may call it a software solution. But the ZGC team didn't choose this solution because dereferencing is very frequent in load barriers. And just one extra instruction can affect performance. The solution provided by the ZGC team is multi-mapping. Each colored pointer has 4 colored bits, but here we do not have to care about the finalizable bit because such pointers are never accessed. And for the remaining 3 bits, marked 0, marked 1, and remapped, only 1 bit can be set to 1 and at the same time, and the other 2 bits must be 0, which means that there are only 3 possibilities for the 3 bits, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So the current solution of ZGC is that they map the real address to 3 different addresses. It's a great idea that now you do not have to dereference before accessing the colored address, because colored pointers with different colored bits point to the same physical address. But this technology has its own drawback, that it can increase DTLB load misses. Another solution is hardware-based. For example, virtual address mask of Spark, top byte ignore of ARMv8, and pointer masking of RISC-V. All these hardware features can be used to mask or ignore the colored bits. Of course, the downside to using these hardware features is that they are not cross-platform. Top byte ignore, aka TBI, means ignoring the most significant 8 bits of the virtual address. So this feature is somewhat similar to the RISC-V pointer masking feature. Therefore, we did an experiment that we tried to implement colored pointer by TBI instead of multi-mapping. TBI only ignores the top 8 bits, so we moved the 4 colored bits from here to here, to the top. We didn't use the 63rd bit only because it has been occupied by stack watermark state. And then we removed the multi-mapping logic. Of course, there are other works to be done to apply TBI to the ZGC, but I'm going to skip the details and let's take a look at the performance. Here is the performance we got. In SpecJBB 2015, we get a 7 to 8% score improvement, and the percentage of DTLB load misses has dropped a lot. But here, I need to point out that the results can vary considerably on different platforms. We get this score on Quimpen platform. Improvements may not be obvious on a platform with a bigger DTLB. We have open sourced the code in OpenJDK 17. You can try it if you want. Things are different when it comes to generational ZGC. The ZGC team is working on generational ZGC, and they plan to release it in JDK 21 to adapt to applications with high allocation rates. The pointer layout of generational ZGC has changed a lot. The colored pointer now has 16 colored bits. So it's not possible to use multi-mapping anymore. TBI also cannot be used to implement such colored pointer because it can only ignore 8 bits, which cannot cover all 16 colored bits. Their current solution is to add an extra dereference instruction, LSR. They put the colored bits in the lowest 16 bits and redshift them in the load barrier. They call the redshift operation as oncolor. According to our test, each extra instruction placed in the load barrier will increase the total number of instructions by 3% in SpecJBB. But with pointer masking, we can move the colored bits to the top of the pointer, and we don't have to do anything for dereferencing in the load barrier. But for now, we only know that every extra instruction in load barrier accounts for about 3% of all instructions. But we don't know how much it will affect performance, because as I just said, TBI is not available on generational ZGC, so we cannot experiment. So finally, people have tried all sorts of ways to implement the tagged pointer, but with RISC-V, pointer masking things seem to be a lot easier. But the problem is it's not a cross-platform. And in summary, today I introduced the work our team have done to port OpenJDK to RISC-V, and I spent the most time introducing RISC-V pointer masking and the experiment based on TBI. Not just use TBI, but there are many other features on OpenJDK. You can try it via the following links, and you can find all kinds of binaries of OpenJDK RISC-V port here. That's what I'm sharing today. Thank you.
Have you heard that? Have you heard the uploads actually for you?
I can see that, but I can't hear that.
All right. Actually, there were uploads. So let's go to some questions. Do we have questions?
Please, question. Hello, my name is Vladimir Kempik. You may see me in RISC-V port mailing lists in OpenJDK. As you said, the intrinsics for vector and ZBA, ZBB wasn't tested on real hardware for performance. Recently, I was able to test ZBA on real hardware with ZBA support, and really, I saw no performance improvement, not significantly. Do you have any plans to test vector intrinsic on real hardware to check their performance? I guess we may see some surprises there.
You mean we should have more experiments on the real hardwares?
Yes,
About ZBB.
Vector extensions and mostly intrinsics for vectors, right? We really need to test it on real hardware, but there is a problem. There is no hardware with vectors 1.0 currently, yes?
Yeah, we don't get the hardwares yet, and we will test the performance on it when we get the hardwares.
Yes. Currently, I have a plan, T-head boards from Alibaba. They have support for vectors 0.7.1. They are slightly incompatible, but I have already adapted some code to at least run some of intrinsics on it, and maybe I will provide some performance data sometime soon.
You mean they are publishing a new hardware? So
yes, I mean,
T-head
boards with older vectors. Yes, but OpenJDK can be adapted to these older vectors. I have done part of this work already, and we may really use T-heads to test performance of vector intrinsics, even if they are older. I will write in mailing list later.
I can't understand you.
Not a kind of a question. It's just like a commentary that there will be some experiments soon. So let's proceed to the next question.
Hello, thanks for your topic. And that's a question which I have. If we use compressed OOPS in the JVM, how it can be combined with pointer masking? Does it will combine it? Where VM stores the additional data for GC, an example, if we use compressed pointers?
No, you can't use compressed OOPs because the ZGC does not support it, and if you use TBI and it's not supported to use compressed address.
Okay, thanks.
So more questions? Oh, we have a question here.
Nihao.
Oh, hi, 你好.
Satya. I have a question about Java 8. Why did you plan to backporting to Java 8? I think that Java 8 is outdated, isn't it?
Yes, it's old, but we at least in China there are many services running on Java 8.
And not only in China, actually, it's
yeah.
It's a whole world problem. Right. So more questions. Yeah, well, actually, we have the question that you mentioned two JDKs, Bijan JDK and just usual OpenJDK, where there is a RISC-V port. So what is the difference between OpenJDK, usual OpenJDK, and Bijan JDK?
Yeah, we have our own hardwares like Quantum CPU, and we did some optimizations for it. And there are some other features. In fact, I'm not very clear about that.
Yeah, so it's well optimized for content hardware, right?
Yeah.
As many features is.
Yeah, there are many features about ARM ARC64 on it.
All right. So there are some features on ARM as well. Okay, maybe the secret one. All right. Any more questions? Yeah, there is one more question.
Thank you for the talk. And the question is, what is your favorite instruction or favorite feature of the CPU which shines in Java? So I guess we kind of have experience with x84 with ARM. And well, while you porting this to a new CPU, what is the favorite feature you are really like?
Favorite feature? Maybe it's pointer masking.
Yeah,
yes. Yes.
Because
it's what right? I'm doing now.
Nice, nice. So do we have any more questions? Then thank you very much again. So this is a close out for you. As you can see.
Thank you. I can see.
Thank you very much for connecting. And now давайте перейдем, в общем, к перерыву перед следующим докладом. Плавный переход на русский. Ну, у нас немножко, наверное, сдвинется расписание, мы чуть раньше закончили, но в целом все равно перерыв 20 минут, после этого начнем следующий доклад. В принципе, если у вас есть какой-то приватный вопрос, вы можете сейчас его спросить, если хотите, но... Ну, насколько это возможно. Многие же выйдут из зала. Вот, соответственно, это будет приватно. So, let's proceed to the break. Thank you very much again. It was great.
Thank you.